We should begin our study of discrete mathematics by looking at logical form. A statement is simply a sentence that is true or false, but not both. So for example, the sentences 2 plus 2 equals 4 and 2 plus 2 equals 5 are both sentences. The first sentence happens to be true, and the second sentence happens to be false. However, x squared plus 2 equals 11 is not a statement, since the truth of this statement, or this sentence rather, depends on the value of x. Combining two or more statements forms what's known as a compound statement. There are three symbols used for this purpose. This sideways looking X denotes not. Depending on the resource you're looking at, you may also see a tilde to represent not. Throughout this lecture series, I will be using this sideways looking L for not. The caret symbol will denote and then this upside down caret will denote or. Now, if we have a set that has more than just one of these symbols, we have to use the order of operations. Negation, the not symbol must be performed first, and we must use parentheses to distinguish the order of and or. So let's look at an example. We're going to let H represent the statement it is hot. We will let S represent the statement it is sunny. The statement it is not hot is sunny can be written in this form. The sideways LH caret S. The statement it is neither hot nor sunny can be written as the sideways LH caret sideways LS. Writing a statement like this is known as its formal form, or writing it formally. We can also represent inequalities as statements. So x less than or equal to a means x is less than a, or x is equal to a. A less than or equal to x less than or equal to b means that a is less than or equal to x, and x is less than or equal to b. And of course, the a less than or equal to x can be represented by the statement above. So let's look at this example. Suppose that x is a particular real number, and we will let p represent the statement 0 is less than x. We will let q represent the statement x is less than 3, and we'll let r represent the statement x is equal to 3. We will write these three statements symbolically or formally. So for the first statement, x is less than or equal to 3. Well, we know that x less than or equal to 3 is the same as saying x is less than 3 or x is equal to 3. Using the statement variables, x is less than 3 is q, so we'll have q. X is equal to 3 is r, so we have q or r. The second one, 0 less than x less than 3. So p is 0 less than x. Well, let's first write it this way. So 0 less than x and x less than 3. Now, 0 less than x is p, so we have p, and x less than 3 is q, so we have p and q. For the third statement, we have 0 is less than x, and x less than or equal to 3, which is 0 less than x, and in parentheses, because x less than or equal to 3 is one statement, x less than 3 or x equals 3. Now using the statement variables, you get p and q or r. Right? The logical connective. So we're going to say that p and q are statement variables. The negation of p is not p. The conjunction of p and q is p and q. The disjunction of p and q is p or q. So negation simply is not, conjunction simply is and, disjunction simply is or. We're now going to look at the truth values of each of these three connectives. And we do this by using a truth table to list all the possible truth values. So we first look at negation. If p is true, then the negation of p is false. If p is false, then the negation of p is true. In other words, negation simply switches a truth value. Looking at conjunction, now this involves two statements. So if p is true and q is true, then the conjunction is true. If p is true but q is false, the conjunction is false. If p is false and q is true, the conjunction is false. If both p and q are false, the conjunction is also false. So the conjunction is true only when both statements are true. Finally, disjunction. If p is true and q is true, then the disjunction is true. If p is true and q is false, the disjunction is again true. If p is false and q is true, the disjunction again is true. If both p and q are false, then the disjunction is false. In other words, the disjunction is false only when both are false. So again, negation simply switches the truth value of the statement. The conjunction is true only when both statements are true. A disjunction is false only when both statements are false. Now this is interesting, this disjunction one. This means in mathematics, this is an inclusive or, which means it allows the possibility for both statements to be true. A statement form is simply an expression made up of statement variables and logical connectives that becomes a statement when actual statements are substituted for the component statement variables. This is a statement form, because p and q are simply variables. This will become a statement if replace P and Q with statements. And as we just saw, the truth table for a given statement form displays the truth values that correspond to all possible combination of truth values for its component statement variables. And as I've just mentioned, in mathematics, we use OR in the inclusive sense, meaning that it allows for both statements to be true. There is also an exclusive OR, which does not allow both statements to be true. The exclusive OR, as statement form, is P or Q and not P and Q. And so this is saying P or Q, but not both at the same time. And we can form this truth table. We have our statement variables, PQ. We have our statement form PQ. We have our statement form PNQ. Now this we're negating the statement form P and Q. So all it does is switch each truth value. And now we're going to take the conjunction of the statement form P or Q with not P and Q. And notice we get our desired result. If both are true, then we get false. If only one is true, we get true. And if both are false, we get false. So what we're going to do is we're going to construct a truth table now for the statement form P and Q or not R. Now here we have three statement variables. So we need three columns for the statement variables. We need a column for P, a column for Q, and a column for R. So for P, we're going to have 4 trues and then 4 falses. Try and short this up. For Q, let's do 2 true, then 2 false, then 2 more true, and then 2 more false. And for R, we'll just alternate true, false, true, false, true, false, true, false. Notice that in general, the number of rows in the truth table will equal 2 to the number of statement variables. So in this case, we had 3. So the number of rows we have is 2 cubed, which is 8. 1, 2, 3, 4, 5, 6, 7. Now the first statement I'm going to look at, P and Q. Let's create a row for that, or a column for that rather. So conjunction between P and Q is true only when both are true. So the first 2 rows will be true. Notice that every other row is false. Now we have not R. Let's take a look at that. Negation switches the truth value. So all we're going to do is we're going to take all of the truth values in the column for R and switch them. So they'll go false, true, false, true, false, true, false, true. We can now form the column for our desired statement form, P and Q, or not R. So we take these 2 columns, we want to do their disjunction, which is false only when both are false. Well, the first two rows has P and Q true, so the first two rows here will be true. Now we have two falses, so it'll be false, true, false, true, false, true. And so this would be our truth table for the statement form, P and Q, or not R. We next look at logical equivalence. We say that two statement forms are logically equivalent if and only if they have identical truth values for each possible substitution of statements for their statement variables. So the logical equivalence of statement forms P and Q is denoted as P equivalent to Q. So this symbol here, it's like a triple E, means equivalent. And we say that two statements are logically equivalent if and only if their forms are logically equivalent. So we're going to determine whether these two statement forms, not the quantity of P and Q, and not P and not Q, are logically equivalent. So what we need to do is we need to construct a truth table. So we have two statement variables. We have P and we have Q. So that means we're going to have 4 rows. True, true, false, false for P. True, false, true, false for Q. So let's look at the column for not first. Negation simply switches the truth value, so it becomes false, false, true, true. Let's do a column for not Q. Again, this switches the truth value, so we get false, true, false, true. Let's now create a column for P and Q, which is true only when both are true. So true, false, false, false. Now let's look at our first statement form, the negation of P and Q. Switches the truth values of this column for P and Q, so we get false, true, true, true. Let's look at now the statement form, not P and not Q. So it's conjunction of the not P column and not Q column. Well, the only row where those are both true is the last one. So we have false, 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 true. In order for these two statements to be logically equivalent, we must have identical truth values. Well, notice the second row and the third row. They are not the same. Therefore, we can conclude that the negation of P and Q is not logically equivalent to not P and not Q. In other words, these two statements do not say the same thing. They're not the same. A tautology is a statement that is always true. A statement whose form is a tautology is called a tautological statement. Likewise, a contradiction is a statement form that is always false. A statement whose form is a contradiction is called a contradictory statement. We will now look at logical equivalences. So for these, we're going to say that P, Q, and R are just statement variables. A bold-faced T is a tautology, and a bold-faced C is a contradiction. The first is the commutative laws. So P and Q is logically equivalent to Q and P. P or Q is logically equivalent to Q or P. So this just says that the and, the conjunction and disjunction are commutative. The order in you write it does not matter. Next up, we have the associative laws. So the grouping P and Q and R is logically equivalent to P and Q and R, and likewise for disjunction. So this says as long as your logical connectives are all the same, your grouping does not matter. Distributive laws, P and Q or R is P and Q or P and R. Likewise, P or Q and R is logically equivalent to P or Q and P or R. So the conjunction distributes across junction, disjunction distributes across conjunction. Next up, identity. If we take P and a tautology, the result is a tautology. If we take P or a contradiction, the result is a contradiction. Negation laws. If we take P or not P, the result is a tautology. P and not P results in a contradiction. Double negation. Not P is simply P. Idempotent laws. P and P results in P. P or P results in P. Universal bound laws. P or tautology results in a tautology. P and a contradiction results in a prediction. De Morgan's laws. The negation of P and Q results in not P or not Q. Negation of P or Q results in not P and not Q. Roughly, you can think of this as you're applying the negation to everything. So essentially, the negation of a conjunction is a disjunction, and the negation of a disjunction is a conjunction. The absorption laws. P or P and Q results in P. P and P or Q also results in P. And finally, the negations of a tautology and a contradiction. The negation of a tautology results in a contradiction. The negation of a contradiction results in a tautology. Verifying all 11 of these laws simply involves creating a truth table like we did in the previous example, and so this will be left for the viewer to do. Now with these 11 equivalences, we can verify logical equivalence in a much simpler way rather than creating a truth table. So we're going to do that to verify that the negation of not P and Q and P or Q is logically equivalent. So in other words, what we want to show that this left-hand side is logically equivalent to the right-hand side. And we're going to do this only using logical equivalences, no truth table. So let's start with the statement on the left-hand side. So the negation of P of not P and Q, and P or Q. Now, we can say this is logically equivalent using property 9. Not P or not Q, and P or Q. So I applied De Morgan's law. Now, I can say this is logically equivalent by property 6, which is the double negation, P or not Q, and P or Q. Now notice here, I have a P or in both statements. So I can say this is logically equivalent by property 3, which is the distribution in reverse, as P or not Q and Q. Which is equivalent by 1, which is commutative to P or Q and not Q. Which is equivalent by property number 5 to P or a contradiction. You have Q and not Q, which is a contradiction. Which is logically equivalent by property 4 to simply P. So we verified the logical equivalence. This concludes this lecture.